Hello and welcome, class. So today we are going to discuss hydrostatic force on submerged curved surfaces. So this is fluid mechanics and I'm Engineer Ronjon Argami. So this time we are going to have the principles and concepts with exercises. So for our learning objectives, at the end of the session, students will be able to first draw and label the free body diagram of submerged curved surfaces, and then apply the concepts of centroid and centroidal moment of inertia in the problems. This is on hydrostatic force on submerged curved surfaces. So for both 1 and 2, we apply the usual thing that we are doing in your engineering mechanics, particularly on statics and dynamics. So number 3, solve problems on hydrostatic force on submerged curved surfaces. So to start with, let us try to imagine when a curved surface is submerged. So it is expected that there is a resultant force P. Now since it is a curved surface, we will have a horizontal component of this P denoted by P sub H, and another component under vertical of this P denoted by P sub V. So as usual, the resultant is computed the way it is the square root of the sum of the squares of these two components. Now, the submerged curved surface could be any of this case. First, we have the surface is above the liquid surface, or the surface is below the liquid surface. So to illustrate this, let us have here a curved portion, of course, that is in between those points, and here the liquid is on the right side. So as we can see, the gate or the curved portion is above the liquid surface. So what is important here is that you know the direction of the force. So the direction of the force is towards left for the horizontal component. And for the vertical component, we have going upwards. It is because the liquid is below your surface, so the liquid is towards your curved surface, and therefore this is the resultant P. And then for the other case, this time the liquid surface is at the left side. So again, there will be value for horizontal component of P, and then the downward vertical force P. So the basis of this direction is the liquid approaching the curved surface, and this will be the value of P. Now the horizontal component is given by the formula gamma H bar A, as usual, wherein our method is just to project the horizontal projection of your curved surface. So therefore, no matter what is the shape of your curve, we will have a rectangular portion for the horizontal component to work in. Say this is the width of the gate or the curved surface. Of course, with that, there will be the center of gravity, as usual, and below that will be our center of pressure, where the horizontal component is concentrated. So, one thing new here is the vertical component of our P, and that is given by the formula gamma volume. So, to get the volume, we'll just have to project the curved surface upwards up to the liquid surface. And the area bounded by that one will be considered. Say, in this case, we have a rectangular portion and a quarter circle. So, the component of the vertical is concentrated on the centroid of these two composite shapes. So here, on the horizontal projection, we still stick to the rule that this is y bar. So y bar is the distance of the centroid up to the liquid surface on the vertical. And then here, y bar is also equal to h bar, since we do not have any inclined surface now, because it is always that your submerged on the horizontal projection is always within the vertical. So therefore, y bar is also equal to the h bar. So likewise, in this case, we label that as a width. This is the center of gravity. Below that is the center of pressure, where the horizontal component is concentrated. So again, this will be our y bar. And then, same procedure for our volume to be considered. Let us project the curved surface vertically upwards up to the liquid surface. And the area bounded by those projections will be the area to be considered in the calculation of the volume. So again, similarly, we have a rectangle and a quarter circle. So this is where our vertical component is concentrated in. And then finally, we get the value of P by the square root of the sum of the squares of your components. And then just the same, this distance is E. So E is the distance between the center of gravity and the center of pressure. So let us try some exercises. For the first problem, find the magnitude and location of each of the components of the force on the curved surface shown in the figure. So as we can see, that this curve is actually a portion of a circle. Why? Because from O to A we have 2 meters, from O to B we also have 2 meters. So therefore, there is a common radius to those lines projected at point of origin. So first things first, we need to project the curve AB horizontally. So this is the horizontal projection. And then we can draw a rectangle out of that. So this is the horizontal projection. And then work with the width that is equivalent to 3 meters. Okay. Say here, we need the center of gravity, and below that is the center of pressure. And then the gate length is 3 meters. And then here, P sub H is concentrated at CP. Now, the usual thing we want is to locate this PH by E. Okay, so in In case that we have a rectangular shape that is fully submerged into the liquid surface, say if we have this the liquid surface, and then this is the gate, and here is the horizontal force, just remember that the pressure is in triangular form. Why is that? Because in our previous discussions, remember that if this is the liquid surface, we have zero pressure at this point. And then as we go down the liquid surface, we say that we add gamma h. So therefore, this pressure distribution starts from 0 up to an increasing value. So that is why that is in triangular form. So this pressure distribution is fully distributed to the submerged portion here, because there is no space for any void to distribute this triangular shape pressure. So therefore, this is gamma h and what would be the essence of knowing that triangular form? So the essence here is if this dimension is h, therefore we'll just have to get the centroid of your triangular pressure. Okay, triangular pressure, this is 1/3 of h, or h all over 3. So isn't it that this location is very much easier rather than to compute for E with the formula I bar all over AY bar. So this is much simpler. If you just know H, if we do know H here, we'll just have to divide that H divided by 3 to locate this horizontal component of P. So the danger in here is this could no longer be applicable to a gate that is over and above its top fiber. So if there should be a space here in between, therefore the pressure distribution will no longer be in triangular form. Hence, the pressure distribution should be in trapezoidal form, wherein we have a larger value of pressure, okay, larger value of pressure at the bottom. So the essence here, what I'm trying to point out is if you have a submerged portion that is over its topmost fiber, this could no longer be applied. Again, with this case, in this case, we are going to locate your pH by your E. So that is below the center of gravity. So we cannot just say that this distance is h over 3 again, because your pressure distribution is in trapezoidal form, while in this one, the whole of the gate is totally submerged just right at your liquid surface. And this concept is also applicable whenever that your gate is partially submerged. So it is partially submerged, if your gate is partially submerged, remember that we are always concerned with the submerged portion only. Hence, that submerged portion is similar to this. We have the center of gravity, the center of pressure, and the horizontal force, pH, wherein this is also H all over 3. So it can be applied to a gate that is partially submerged but would no longer be applicable to a gate that has space between the top fiber and the liquid surface. So this is the simple explanation to that. So in this case, so let us locate our pH, where pH is actually the head all over 3. So in this case, we do not know yet the value of this height, head of the gate. So if I'm going to label this as X, therefore this is X all over 3. So we wanted to determine the value of X for the sake of H bar, because H bar can be used on the formula of the horizontal pH. So as you can see, we have here a triangle OA. So I'm going to label this as point C. At triangle AOC, we can relate the function of X and then the hypotenuse AO and then the angle 60 degrees. Notice that X is opposite the angle known, that is 60 degrees. And we have the hypotenuse, so therefore we are using opposite and hypotenuse, so therefore we take the function of sine, and then opposite to sine is X, and the hypotenuse is 2 meters. Hence, by cross multiplication, X would be equal to 1.73 meters. Now, as you can see, H bar is just the half of your X, because that is the center of gravity of a rectangle. We just use half of the dimension. Here we have H bar is equal to 1.73 all over 2. And that will be equal to 0.865. Okay? So, let us have now our pH. Say we have here letter E. We have pH is equal to gamma H bar A. So gamma is 9.81 kilonewton per cubic meter. H bar is 0.865 and the area is 3 by 1.73 meters. So therefore, the horizontal component would yield to 44.04 kilonewtons. And then for each location, it is how many meters from point A. So we are going to locate your pH from A. And that is X minus X all over 3 below A. So when we substitute that one, we have 1.73 minus 1.73 all over 3, that is 1.15 meters below A. Now, as we can see on the first procedure, we are just concerned with the horizontal force, which we have done last time. The only difference is when we have a plane surface that is not a curve, a plane surface, you may consider the area whether it can be inclined to a certain degrees or vertical. But this time, if we have a curved surface, we always project that horizontally. So therefore, it is always that we are working with a rectangle if we have a curved surface. And this rectangle will be our basis in computation for the horizontal component of your P. Okay, so moving on to the next step. Of course, we are done with the horizontal force. We have already located the horizontal force. So this time, we are now concerned with your curved surface. Say this is your curved surface. Say your curved surface is from point A to point B. So all we have to do is to project that upwards up to the liquid surface. So projecting that upwards up to the liquid surface, we will be having here an area in the form of spandrel. So the shaded portion can be computed by the trapezoid, say if I'm going to label this as point D. So the trapezoid, so here's the trapezoid. OADB. We can subtract this to the area of this portion of the circle. Say minus circular sector OAB. So the difference of this one is actually what we are trying to compute, the area bounded by the curve projected upwards up to the liquid surface, and that is equal to the portion, spandrel section ADD. So this is actually the area we need to know in order to compute for the vertical component of P. So let us do it. So for our trapezoid, we have 1/2 base 1 plus base 2 times the height x. So the height of this trapezoid is x, and then minus, so in here we are going to get the proportion of the circular sector to the whole circle. So the formula for circle is pi r squared, right? And then we multiply this by the ratio of your angle theta all over 360 degrees. Say I'll just label this as the area of ADB. So from this, we can have this to be 1/2. The upper base is 1, the lower base is 2, x is 1.73 minus pi times 2 squared. So we move this for a while. Then angle is 60 all over 360 degrees. So we can compute this to be area of ADB. Hence the area will be equal to 0.51 square meters. So to make it as a volume, we need to multiply this by the width of the gate, which is 3 meters. So the volume is area times length. We have 0.51 times the length of 3, that is equal to 1.53 cubic meters. So knowing this volume, we can now have our vertical component of P. Say we have letter B, we have PV is equal to gamma times volume. Hence, PV is equal to the unit weight 9.81 times the computed volume 1.53. So that would yield to 15 kilonewton. So therefore, this will be the value of our PV. So the next thing we wanted to know is the location of this PV from A. So what we do here, since we have a strip of area, we cannot really directly use a formula of spandrel, since this spandrel is just a part or portion of this curve. So what we do is do it by integration. So we leave some spaces here, and we'll compute the location of PV by integration. So the usual thing we want in integration is that we get a strip element from this whole portion, or the shaded portion. Say this would be our strip, and then we refer this to our point of origin. Say we will use our reference point O here. So the strip up to point O, say we label that as Y, and if that would be Y, the small strip here shall be dy. We can now write our integration equation. So basically, in every formula for x bar, say for example, we need to determine the centroid of this one. Say this should be our centroid. So this centroid can be located from any of the side or from the horizontal, along the horizontal, and then up to the corner. Say this is x bar. So the formula is area times x bar is equal to the integral of x times the differential area. So that this differential area refers to the differential element that we have formulated, or the strip out of the whole area. So in this case, since we have labeled this as y, therefore the centroid of this one should be y bar. So in here you can notice that our strip, or this element here, the yellow element here, has horizontal distance from your reference O. So basically, you also need to establish a vertical distance from point O to complete your variables in the integral equation. So I'll just label this as z distance from point O. So this element has now reference horizontal distance from O and a vertical distance from O also. So therefore, we are now ready to write our equation. So referring to this equation, we can say that we have area. Instead of writing it as x bar, we have labeled that as y. So therefore, we will just have to write this as y bar. And then that is equal to the integral of, so we need to establish a limit of this integration. So what would be the limit if we refer to point O? Since the element is referred to point O, we need to integrate in a certain range. Say from 0, we will start to integrate at this point, because the start of this red area here starts from point A, and point A is within 1 meter. So basically, this is 0 up to 2 meters, and then the integration will start at point A. So this is 1, that is 1 meter, and then that is 2 meters. So we integrate it from 1 to 2 to complete the whole red area here. Say we just place it in here. Integration range is 1 to 2, and then our x here would refer to the horizontal. So in your figure, your horizontal distance is y, and then your differential element area is dy times this distance, because this distance is the height of this element and the base of the element is actually dy. So looking at the dimension, we can say that x is the whole dimension of these two. So therefore, this distance is x minus z, wherein x is 1.73. So we just place it there, x minus z, and then the base is dy. So therefore, base times height, it's just dy times x minus z. So this is the area of this differential area here element from the state. Okay, so this completes our equation, but we need to express your equation in terms of a single equation in terms of dy or y under the function of y, so that we can evaluate our integrand. Now to do that, we know that x is 1.73, so we'll just copy that and then we just replace x by 1.73. So in here, we still need to express z in terms of y so that we can finally integrate. Okay, so what would be the relationship of z and y? So if you notice, if we are going to pick from the dimension, so this is the point where z is referred to and y is referred to, and this point is within your circle. So we agree that from point O up to that point, this is also 2 meters. So therefore, at any point in the circle, from the point of origin, this is a point, this is radius, and then another point that is radius, and then another point that is radius. As long as the radius is inclined with the horizontal, there will be a corresponding y for this radius and x for this radius. At any point, there is a radius and there is a corresponding x and a corresponding y. So notice that x and y are the legs of the hypotenuse radius. So therefore, if you would recall, the relationship of the radius to those of the legs will be in Pythagorean theorem. We have r squared is equal to x squared plus y squared. So in this case, if we are going to utilize this relationship by this point, of course, we can say that 2 squared, so the hypotenuse or the radius, will be equal to, what would be the horizontal distance here? Y squared, and then the vertical distance here is z from the drawing. We just place it here, and then we have to solve for z, where z will be equal to square root of 4 minus y squared. So this shall be substituted in this equation so that we will be having only single variable on your integrand, that is y. So we simply replace z here, and then of course all in terms of y, we can now evaluate your integrand. So we know that area here was already in place. We have 0.51, and then if we are going to evaluate this integrand, that would yield to, we have 0.863. So with that evaluation, we can just divide 0.863 divided by 0.51 to come up with the value of y bar. So we can have y bar is equal to 1.69 meters. So y bar is 1.69 meters from point O. So if we are concerned with the distance of PV, okay, of PV to that of point A, we'll just have to subtract 1 meter. So y bar minus 1 meter is the distance of our PV. See, if this should be our PV from point A will be 0.69 meters plus 1, that is y bar actually. So 1 plus 0.69 y bar, 1.69. So the distance from PV to point A is 0.69. So this PV is 0.69 meters right of point A. Okay? So that ends this problem. Okay, next, for the second problem we have shown in the figure is the section of the hull of a ship having a curved portion in the shape of a parabolic arc with vertex at point B. If the length of the ship is 5 meters, find the total force against the curved surface AB. The unit weight of seawater is 10.10 kilonewton per cubic meter. So in here, as usual, we project the curve AB horizontally first. So we treat it as a plane surface along the horizontal. And then, by the way, we have a dimension here, 3 meters and 2 meters. So this is a part of the given. So at any rate, we know that the width of our ship, or the length of the ship, is 5 meters. So therefore the base of this rectangular is 5 meters in dimension, and then we tag this as the center of gravity, and then the center of pressure where our pH is concentrated. Notice the direction. Okay, the direction is from liquid towards the curved surface. So this is the liquid, this towards the liquid, or towards the gate or the curved surface. So we can easily deal with our pH by the formula gamma H bar A. And then gamma here is 10.10, then the H bar is from the center of gravity up to the liquid surface, and that will be equal to, so the half of 2 is 1 plus 3, that is 4 meters. So therefore, given H bar is equal to 4 meters, we have 4 times the area of this rectangle, 5 by 2. So we get all of the product. pH equal to 404 kilonewtons. So we are done with the horizontal component. Let us now proceed to the vertical component. So in this case, the surface is above the liquid surface. So if this is the liquid, and the liquid is towards the curve, so therefore our PV should be going upwards. Say this is our PV. So we can easily compute PV by the formula. PV is equal to gamma times the volume. Say we have 10.10 as for our gamma, and the volume is a composite area for a rectangle and parabolic segment. So for a parabolic segment, if we have a rectangle here and the parabolic curve here, this is second degree, the area of this region is 1/3 base times height if this is our base and this will be our height. Now the unshaded boundary here will be, of course, 2/3 base times height, so that if we add this one, we have the area of rectangle equivalent to base times height. So in this case, we have this one to be 2/3 base times height, and this, we treat this as a rectangle, that is length times width. So therefore, all of this area will be totaled and then multiplied by the width, that is 5 meters. So we place here the area of the parabolic segment, that is 2/3 times the base is 1, the height is 2, and then we add the rectangular portion, we have 1 by 3. So this will be enclosed by a bracket and then multiplied by 5 meters, which is the width of our ship. So therefore, that would yield to 218.67 kilonewton. Now that we know our horizontal component and the vertical component, we can now solve for our P. So our P is actually the result or the mother force of these two components, and it can be computed by this formula. So we just substitute the values and then we have P is equal to 460 kilonewton. So this will be the required in the problem. So on the problem, it does not require us to locate the horizontal components.